As we begin chapter 3, we start looking at some applications of derivatives in a different sense that we looked at applications at the end of chapter 2. To begin with, we're going to look at analyzing functions, analyzing graphs, and things like that by using what we know about the slopes of tangent lines, what we know about derivatives, and so forth. So in the first section, we're going to look at finding extrema. And specifically, we're going to look at finding extrema on intervals. But we can also find some extrema whether we're given a particular interval or not. But when we talk about an extrema, we're talking about a maximum value or a minimum value. When we say maximum or minimum, that can have a variety of meanings. So when we say max, that could be the absolute maximum value, meaning that for our function, it could be the highest point that our function has anywhere, or it could be a relative maximum, or sometimes instead of calling it a relative, we call that a local maximum, and that means that it's higher than points surrounding it. So if I look at this sketch here, this point is not the highest point on the whole graph. There are points that go above it because this graph goes up forever. But if we look at it in comparison to things that are near it, then that point is higher than everything around it. So locally speaking, that's the highest point. Sometimes I use that example that if you look at where your house is located, compared to your neighbors, you might be at the highest point in your neighborhood, but you might not be at the highest point in the entire town. Or even if you are at the highest point in your town, you might not be in the highest point in your county or your state. I don't think there are any houses on the top of Mount Everest, so your house is not at the highest point on Earth. So there are points higher, but just in consideration of things near it, that's the highest point. So we would consider that a local or a relative max. At the same time, this point here is not the lowest point on the entire graph, but relative to what is around or in its location, it is a minimum. So this is a local or a relative minimum. Some graphs, for example, this graph does not have an absolute maximum or an absolute minimum because it keeps on going up and it never stops going up, it never stops going down. Sometimes there are points that are both an absolute and a relative maximum. For example, if we have a parabola or something similar to a parabola, this point, if we just look at what's around it, this is a local minimum. But it's also the lowest point on the entire graph. So a local minimum can be the lowest point on the entire graph, an absolute minimum, but it doesn't have to. If we were to take a turn and do something like this, then that would only be a local minimum. It would not be an absolute minimum. Now, it gets more complicated on whether it's an absolute max or minimum when we use our entire domain. But if we only look at a certain interval, then that may be easier to determine. So we might have this function, and this point might be, of course, it's not the absolute minimum of the entire function, but if we restrict our interval to be, let's say, here. Let's say we go from A to B, whatever those x values are, then in this interval that goes from A to B, this point is the lowest point. It's lower than any point on the entire interval, so that's the absolute minimum for that interval. At the same time, this point, that's the absolute highest point on that interval. Now notice that one's not at a peak or at a trough like this one, or if we were looking over here, this maximum, relative maximum, would be at a peak. So when we're dealing with an interval, specifically a closed interval, and when I say a closed interval, that means that we are including the left and the right edges, then our maximums and minimums are going to occur either on the edges or at some interior point. So the first problem that they give us, let me move this. They start out by asking about the value of a derivative at an extreme point. So notice this point is, it looks like on this function it's an absolute minimum, but it's at least a local minimum. So they want us to find out what is the value of the derivative at that point. And remember what a derivative tells us. The derivative is the slope of the tangent line at that point. So if we need to know the value of the derivative there, let's take the derivative. Now, we could actually do this without the derivative, but just to verify, let's take the derivative. So we have a quotient. So if the numerator is u, if u is x squared, then u prime would be the derivative of x squared, which is 2x. If the bottom is v, then v prime would be 2x. That's the derivative of the bottom. So remember, we don't just simply take the derivative of the top and the bottom, but we have to use the quotient rule. U prime v minus u v prime, all of that over the bottom squared. So u prime is 2x, v is x squared plus 4, minus u times v prime. All of that over the denominator squared. Now typically we would go through and we would simplify that, but since we're just looking for the value of our derivative at one point, let's just plug that in. So we want to know what is the value of the derivative when x is 0. So let's plug a 0 into our derivative. So we're going to have 2 times 0 times 0 squared plus 4 minus 0 squared times 2 times 0 over 0 squared plus 4, and that all squared. So notice the first term, we have 2 times 0 times 4. Well, anything times 0 is 0. And then for the next term, we have 0 times 0, which is 0. So we get 0 on top. We get 4 squared, 0 plus 4, that's 4. So 4 squared on bottom. And 0 divided by 16 is 0. So at x equals 0, our derivative makes 0. So remember, again, as we said, what does the derivative tell us? It tells us the slope. So at our extreme point, our slope is 0. Notice if we draw a tangent line through that point, we have a slope of 0. So that's going to be typically what happens. If we have a minimum or a maximum, then at that minimum or a maximum, our first derivative is going to be 0, because we're going to have a horizontal tangent line typically when we have an extrema, a relative minimum or a relative maximum. Now, there is another instance, and that's when when we have an extrema that looks like this. And I believe we discussed back in chapter 2 that if we have a function that looks like this, then at that point, our first derivative is undefined. And we discussed why that is. We said that looking from the right side, it looks like we would have a slope that's positive. If we approach that point from the left side, it looks like we should have a slope that's negative. So we're approaching a different tangent line from different sides. So our tangent line has an undefined slope. We don't really know what the slope of the tangent line is there. So where our first derivative is either equal to 0 or undefined, we refer to these as critical points. Critical points. So anytime you hear me say find the critical points, that's where the first derivative is 0 or where the first derivative is undefined. There are some exceptions, but typically when the first derivative is 0 or the first derivative is undefined, that's typically going to be some type of extrema. So the next question that we're going to do asks us to find the critical numbers for this function over this interval from 0 to 2 pi. So to get the critical numbers, we need to take the derivative. Well, our function sine squared x, that's best interpreted sine of x squared. Of course, we rewrite it like that because we have to use the chain rule to take this derivative. So to take the derivative of that, the outside function is x squared. So we bring the 2 down. We do sine to the 1 less power, and then times the derivative of the inside. The derivative of the inside is cosine. And then we take the derivative of the other term. The derivative of cosine is minus sine. So our first derivative is 2 sine x cosine x minus sine x. And our critical numbers occur where our first derivative is 0 or where it's undefined. So this function is not going to be undefined anywhere. We don't have a fraction. We don't have a radical. And sine and cosine are continuous functions. There aren't values that make sine or cosine undefined. So we can only find out where this is equal to 0. So if we have this equation, we have more than one trig function. So we need to have a 0 on one side and we need the other side factor. So on the left side, we have a common factor. We can factor out a sine. So that's going to leave us 2 cosine x minus 1 on the inside. And then we set each factor equal to 0. And remember, we're only looking for values between 0 and 2 pi. That means in the first rotation. So in the first rotation, when is sine 0? Remember, on the unit circle, sine is the y-coordinate. So the y-coordinate is 0 here and here. So sine is 0 at 0 radians and at pi radians, 0 and pi. Now for this other one, we would add 1 to both sides and then divide both sides by 2, so we would get cosine is 1/2. Cosine is positive in the first and the fourth quadrants. So if we look at the first quadrant, if we look at the 3 ordered pairs, if you go to your unit circle, the x-coordinate cosine is 1/2 here, and that's at pi over 3. And in the fourth quadrant, cosine is 1/2 here because the x is 1/2 here. In the fourth quadrant, I believe that's 5 pi over 3. You can check me by pulling that up on your unit circle. So these are the values for which if we were to graph this function, we would get our critical numbers. This is where our slope is equal to 0. That's where we set our first derivative equal to 0, which is where our slope equals 0. So those are our critical numbers. All right, so the next several problems, they want us to look at finding absolute extrema, but not over the entire domain, over a particular interval. So I've got somebody asking me a question. Let me pause real quickly. All right, so I showed us a graph earlier that looked something like, I don't know exactly what we did, and ours might have been backwards from this. And I said that a certain point was the lowest point in its area, but it was not the lowest point on the entire graph. So if we have a closed interval, let's say it goes from here to here, then our maximum and minimums will occur at one of two places. They will occur either on the edges. For example, notice on the right, our graph is going up, and we're stopping here, but our graph kept on going up. And that point is higher than anything around it. It's definitely higher than these points because to get there, we're going up. But it's also higher than the other side, and it's higher than anything in the middle. This point, it's lower than the other side, but we have a point that's lower. We have a point here that's lower. So our extrema will either occur on the edges or it will occur at a critical point. How do I know that's a critical point? Because if I go down and then I have to go back up, I go from a negative slope to a positive slope. So at this location, I have a slope of 0. So I've gone from decreasing to increasing. So where I change from decreasing to increasing, I have a slope of 0. So that's a critical point. Sometimes they're called critical numbers, sometimes critical points. So our extrema occurs on the ends or in the middle. So what are we going to do? We're going to test left side. How do we test a y value? We plug the x in and we find out what y goes with it. So when x is -4, y is 5 minus -4, or 9. On the right side, if we plug a 2 in, y is 5 minus 2, which is 3. And then we need to see if we have a critical point inside our interval. Now, if there are no critical points inside our interval, then there's no place we change from going down to going up, or from going up to going down. So if there are no critical points inside the interval, then our extrema will be on the edges. So how do we find out if we have any extrema? We take our first derivative. If we have any critical points, we take our first derivative. So the derivative of 5 is 0. The derivative of x is 1, so our first derivative is -1, which that's not possible for that to be 0. The first derivative, the slope of the tangent line, is always -1. It's a constant. Why is that? That's because our function is a straight line that has a slope of -1. So since we have no critical point, our extrema is going to occur on the edges. So the left edge, our y value is 9. The right edge, our y value is 3. Which of those is the largest? Well, this one. So that's our absolute maximum value on the interval. This one is the smallest, so that's the absolute minimum value on our interval. If we just sketch this real quickly, we draw an x and y axis. Our graph has a y-intercept of 5, so up 1, 2, 3, 4, 5. We have a slope of -1, so it's going down. So down 1 over 1, down 1 over 1. If we go to the left 4 units, we would go up 1, left 1, up 1, left 1, and we would keep doing that. So our straight line looks like this. So we said it's a straight line that goes from -4 over to 2. Notice the left side is the highest point. X is -4, y is 9. And the right side is the lowest point when X is 2, y is 3. So absolute maximum, absolute minimum in that interval. So let's do the same thing on the next one. So let's go ahead and find our critical point first. So if we take our derivative, we're going to need to do the quotient rule. So if u is the numerator, then u prime is 4x. If v is the denominator, then v prime is 1. So our derivative is u prime times v minus u times v prime over the denominator squared. So if we distribute on top, we get 4x times x, so 4x squared. 4x times minus 6, so minus 24x, minus 2x squared, all over x minus 6 squared. There's no need to distribute the denominator, leave it factored. On top, we have 4 minus 2, so we have 2x squared on top, minus 24x over x minus 6 squared. And let's go ahead and factor that numerator. So we have a common factor on top of 2 and of x. So that's going to leave us x minus 12. That doesn't reduce. But the reason I wanted to factor that is that's going to make life easier when we get our critical points or our critical numbers. When we set this equal to 0, notice we have a fraction equal to 0. Now, if you wanted to, you could clear the fraction by multiplying both sides by x minus 6 squared. If we multiply the left side by x minus 6 squared, those would cancel. And if we multiply the right side by x minus 6 squared, 0 times anything is 0. So we would get 2x times x minus 12 equals 0. That's perfectly fine to do. But if we have one fraction on the left and we have a 0 on the right, the only way we can make a fraction equal to 0 is whenever the numerator is 0. So if we just take the numerator and set it equal to 0, we have already factored the numerator. We did that in the previous step. So since that's factored, all we have to do is set each factor equal to 0. So we have a critical number when x is 0 and a critical number when x is 12. So those are our critical numbers. Now that's for our entire domain. But our interval is only -3 to 12. So when we're looking for the extreme in that interval, we need to know what are the y values on each edge and at any critical number that's inside the interval. So our critical number, or our critical point inside the interval occurs when x is 0. So we're going to substitute a 0 into our function to get the y value. The slope, how do we know the slope? This number came from setting our derivative equal to 0, and remember our derivative equals slope. So we found out when our slope is 0. So at this value, the slope is 0. We want to know the y value. So if we substitute 0 into our original function, we can find the y value here. So 0 squared times 2 is 0. So we get that when x is 0, y is 0. We also need to know the y value at each edge of our interval. At -3, we get 2 times -3 squared over -3 minus 6. So -3 squared, that's 9, 18. Gives us -9 on bottom, for negative 2. So when x is negative 3, our y is negative 2. And then the rest of our interval has an x of 2. So let's substitute a 2 in. So we're going to have 2 times 2 squared over 2 minus 6. So 4, 8 on top, negative 4 on bottom. So negative 2. So when x is 2, y is negative 2. So on our interval, just briefly sketch, we might not know exactly what it looks like. But our interval goes from negative 3 to 2. So 1, 2, negative 3 to 2. When x is negative 3, we're down 2. When x is positive 2, we're down 2. And when x is 0, y is 0. So our graph is doing something like this. Remember, our interval goes from here, negative 3, over to 2. Again, it's a closed interval because we are including the edges. If it didn't include those edges, then we would call it an open interval. So this is closed. We include the edges. So we have a maximum value here at 0, 0. And notice our two edges, our left side and our right side, those are at the same y values. Those are at the same. So we actually have two minimums. We have a minimum at negative 3, negative 2, and we also have a minimum at 2, negative 2. Those are each the lowest point in our interval. So for this interval, this is the absolute highest point, and these other two are the absolute lowest points. Let's look at one more problem. And in this problem, notice that some problems we're given an interval, or some pieces we're given an interval that's a closed interval, but not every interval. This interval is open on one side. What do I mean by that? 4 is not included in the interval. We get close to 4, but we don't include 4. On part C, we don't include either end. We include what's in between there, but we don't include 0 or 8. So we need to find out how are we going to treat these differently, or how does that affect the absolute maximum and minimum values in those intervals. So let's start out by getting our critical points. So if we take the derivative of our function, we get 2x minus 8. If we set that equal to 0, add 8 to both sides, and divide by 2. So our critical point is when x is 4. That's our critical point, and that's the only critical point that we have for this function anywhere. So the critical point is x equals 4. So now if we look at part A, we need to find what f of negative 1 is. We need to find out what f of 8 is. And our critical point is in that interval, so we need to find what f of 4 is. If the critical point was not in that interval, then it would be of no concern. So when we plug a negative 1 in, negative 1 squared is 1. Negative 8 times negative 1 is positive 8. So on the left side of our interval, our y value is 9. When x is 4, 4 squared is 16. Minus 8 times 4 is negative 32. So y is negative 16. And if we put an 8 in, 8 squared is 64. Negative 8 times 8 is negative 64. So we get a y value of 0. So just a quick little sketch here. When x is -1, we're up to 9. When x is 4, we're down to -16. And when x is 8, we're at 0. So if we go through here, our maximum value for this interval is 9. Our minimum value is here when x is 4 and y is -16. So it says, what's the minimum? The minimum is 4, -16. What's the maximum? The maximum is -1, 9. We don't have to have a picture to do that. The picture is just to help us visualize what's going on. But when we check our endpoints, our left and our right side, and then our critical point, the one that's the largest value is the max. The one that gives us the smallest value, that's our minimum. Now let's look at part B. Part B goes from 4 to 9, but technically we don't include 4. So let's find f of 9 to begin with. If we put a 9 in, 9 squared is 81. Minus 8 times 9 is minus 72, so we get 9 for that. Now, what happened at 4? 4 was a critical point. So inside our interval, there's no critical point inside the interval. No critical point inside the interval. So our maximum and minimums will occur either on the right side, the left side, but not in the middle because there are no critical points in the middle. Well, let's remember that at 4, even though we don't include 4, our y value is -16. Now, why did I even mention that? That helps me determine if the other side is going to be a maximum or a minimum. I need to know, is the y value at 9 higher or lower than the y values on the other side? If we sketch this graph, when x is 9, we're up to 9. We don't include when x is 4, but when x is 4, we would be down at -16. Remember, the only difference between a parenthesis here and a bracket here is that for a bracket, we do a closed circle. For a parenthesis, we have an open circle here. There's no critical point in between, so there's no relative max or relative minimum in the middle, so we just go kind of towards that. It's technically slightly curved, but there are no peaks or troughs in between there. So our only values of interest are on the edges. There's no critical point in the middle. So do we have a maximum? And the answer is yes. On the right side, that's the highest point on the entire interval. So our maximum is the 0.99. Do we have a minimum? If this point was included, if there was a bracket there and that was a closed-in circle, then yes, there would be a lowest point. But remember, when we have an open circle, we get closer and closer and closer and closer to that point, but we never quite reach there. So each successive point is getting lower and lower and lower. We don't quite reach that point, but we also don't reach that minimum value. Normally, when we would think that there's no minimum, we would think that it goes down towards negative infinity forever. Here, we're going closer and closer to -16. We don't quite reach -16, but we also never stop going down. We're getting closer and closer and closer to -16, but we never stop going and we never quite reach there. So technically, the minimum does not exist. Where the minimum would actually be, that point is not included in our interval. So a maximum, but no minimum. All right, let's look at 0, 8.
So even though 0 and 8 are not included, let's go ahead and find f of 0. So 0 squared minus 8 times 0, that's just 0. If we plug an 8 in to our function, we already found out that when x is 8, y is 0. And we do have a critical point in this interval. Remember, x equals 4 is our critical point. So when x is 4, our y is negative 16. So if we just sketch that, when x is 0, y is 0. That point is not included, so there's an open circle there. When x is 8, y is 0. That's a parenthesis, so that's an open circle. And then when x is 4, we're down to negative 16. And at that point, that's our critical point, so that's where we have a horizontal tangent line. So what about this one? That point, even if we don't have the graph, notice negative 16 is lower than either edge. Negative 16 is lower than either edge, so that's a minimum. This is smaller than either of these. Now, if these edges were included, then both of those would be maximums. If we had that colored in and that colored in, then those would both be the highest points for our interval. But since they're not included, like the previous explanation, since we get closer and closer to those points but we don't quite reach there, we never stop going up. We're not going up very much, and we don't go over 0, but we don't quite reach that highest point, so there is no maximum. The maximum doesn't exist. Because where the maximum would be for the interval, those points are not included. All right, lastly, let's look at the interval 4, 10. So when x is 4, that's negative 16. And remember, x equals 4 is our critical point. So inside the interval, there's not a critical point, just on the edge. If we evaluate 10, we get 10 squared is 100. Minus 8 times 10 is minus 80. So when x is 10, we're at 20. So if we included both of these points, this would be the minimum, this would be the maximum. But this point is not included. We don't include when x is 10. So we only have a minimum. We have a minimum of 4, negative 16. But for the maximum, it doesn't exist. And again, we'll sketch that just for reference. So when x is 4, we're down to negative 16. When x is 10, we're up to 20. There are no peaks or troughs in between there. For our interval, we include 4. We don't include 10. So we have a minimum, we have a lowest point, we don't have where the highest point is. Again, we can do that just from looking at these numbers. We needed to plug both of those x's in for comparison, even though technically this point is not part of our interval, it just gives us something to compare to. So this point is lower than that one, so this is going to be the minimum, not the maximum.